Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about NASA ISRO Synthetic Aperture Radar or NISAR. So let's dive right into it. Now, what exactly is this? Basically, this is one of those things that is huge. Like for a synthetic aperture radar, this is the hugest we have in space looking at Earth. So this is a big puppy. That's why I had this image. Like this is huge. Like most of R&D just went into making this dish, and that's why you will see this dish animation going on for like years ago. That's the whole point. Like more, like same way, James Webb Space Telescope have that unfurling sun shield. This is the same puppy. Like very complex. Like majority of the R&D went into this. Then we come to polar sun synchronous dusk to dawn orbit. So it's gonna rotate like where sun is here, is gonna like I'm Earth, sun is like is going like this. Now it does not matter whether it has to be in sun synchronous orbit. It's not dependent on optical phenomena, but that's the orbital height that was chosen. Now why this is such a big deal is simply because this is first dual frequency. There are many satellites that are this thing, but this is the one of those puppy that has a huge dish. On top of that, it can do two frequency at the same time. That is mind-boggling. And its core focus is on land and ice sheet. You have to understand, we have different satellites. Each satellite have its own core group. For example, there are satellites that sole job is, hey, I'm going to focus on vegetation. There are satellites whose sole job is, I'm going to focus on water bodies. There are satellites that's, core focus on atmosphere. So there is one power missing, land. Nobody was studying land. What's happening to the basic land? What the hell is happening here? So this puppy is there, and it also gives the ability to study ice sheet. How the heck ice sheet is moving, it can be scanned and studied. And this puppy is big, fast. What does that mean? That simply means it can do global coverage, meaning it's gonna make a globe data in 12 days. That's fast. Basically, it can easily make 2, 3, 4, planet captures, planet snapshot every month. So almost 4 snapshots per month. So it's mind-bogglingly fast for the amount of throughput it has. And it's a big daddy project. So it has two major partners, that is NASA and ISRO. And you will get image something similar to this. Now be mindful, this is a false color. You can change the color to whatever you want, and this is a two-dimensional data. There are other dimensions also, like polarization. If you want to collaborate that data into this, you may find a rainbow color kind of image that generally has polarization data. May not be useful for you and me, but it's really useful for people who know what that is. So this is what we are talking about here. So the marriage that happened here is basically allowed this puppy to become the world's most expensive Earth observatory. Are there other expensive things? Yes, ISS is like bitch please. And what about James Webb Telescope? That again, $10 billion. This puppy all easily is expected to cross 1.5 billion, because be mindful, you can only know about the capital cost that went into making this. Running cost is a separate different thing. So that's why NASA spent around $800 million into this, and ISRO spent $99 million on it. So what did NASA give? NASA gave L-band 1.25 gigahertz 24 centimeter wavelength radar. Like who gave the L-band? That's NASA's job. Now again, this thing requires a very precise clock. So world's best precise clock? GPS. So GPS receiving system is directly placed into the. Now because it's not only giving you two-dimensional data, basically X, Y, and how high something is, it's not giving you a two-dimensional map. It has other data also, polarization and all that jazz. So data throughput is huge, and given the fact it's scanning entirety of planet, it needs 3.5 Gbps Ka-band basically telecommunication backlink. It's huge. And even the SSD that is going into this puppy is huge. It's as in like terabytes of data per day, kind of huge. So it's big beefy boy. And the main reason, the cream of the crop, that's 12-meter deployable mesh antenna, that big puppy. Now, what is ISRO doing here? ISRO is providing S-band. S-band is 3.2 gigahertz, meaning the wavelength is much smaller, 9.3 centimeter. Now, be mindful, every wavelength has its pros and cons. That's why ideally you want to have every wavelength. You want to have ultraviolet, you want to have infrared, you want to have optical, you want to have microwave, you want to have X-ray, everything. So here they are focusing on two, 24 centimeter and 9.3 centimeter. Benefit of 9.3 centimeter, you can only see things that are like bigger than your wavelength. You cannot see like much smaller than your wavelength, half at best case scenario. Like if you are, let's say 10 centimeter, your best case scenario, you can only see something that is 5 centimeter. You cannot see something that is in millimeters. That's required. So if you really want to see something small, you have to use wavelength that are small. So 24 centimeter has better penetration, meaning foliage, it can go deep. Like soil surfaces, it can go deep. 9.3, it can give you resolution. So it's basically doing penetrative radar and scanning radar at the same time. And it's going to use GSLV Mark II for launch vehicle and service provider. Basically, after launching, whatever needs to be done, it will be done by ISRO. And ISRO is also providing the satellite bus, meaning whenever you're talking about big ass satellite, generally most of the time nowadays, It's not a new satellite. Anytime you see a satellite, generally there is a bus that has been bought by whatever company that you are dealing with. So there is a bus, and you just put, I want to put spy equipment, you put on spy equipment. You want to put a radio telecommunication, you put radio telecommunication. That's up to you. You have a bus and you put things on it. So NASA is providing basically the hardware, the like basically brains of the operation. Who is providing the backbone? The backbone is Insta3000. I have no idea who the heck named it, but that's what it is. Insta3000 system. Now this puppy is gonna, the main bus is gonna dock with the basically rocket. It's gonna be put on there, and it's gonna provide the power, 6.5 kilowatts of power. This puppy is energy hungry. And this puppy landed on India, so it's now on ISRO's hand. And you can see family is very happy with this marriage. It was awesome. ISRO and NASA getting together, that's awesome. Everybody is happy with this. Then we come to the technology of it. And I did say there are like two major partners. There are other partners also. The reason for other partners, it has one of the most magical technology I ever heard of is Sweep SAR technology. What does that mean? That simply means that technology was developed by Jet Propulsion Lab and German Space Agency. That's why I specified. There are two major partners, others are also there. German Space Agency specifically. Now, what does this mean? This simply means you have to understand radar. When you are doing a radar, it's almost acting like a LiDAR. You yell and you listen for the time. Ping, basically. Twing. You listen to it. That's all you do. Now, what does it give you? All it gives you is one-dimensional data. Is like how far something is. That's useless. So what do you do to take that 1D data and make it into 2D data so you can put an image? You put your data into it. Basically, where was I when I had this event? Like stopwatch. A stopwatch is not only used to measure basically how far where I was, and you are in orbit, so you're moving. So that gives you one other data. It's like at let's say 12 o'clock I was here. At 12:01 I was here. That gives you another data, two-dimensional data from your location and distance. Now you have 2D data. So that's how you do it. Now, how big of a land area it can scan? This is where the amazing part happens. 240 kilometers in one scan. Basically, one pulse of this can scan 242 kilometers. Huge. And one thing you have to understand, because all it's doing is receiving back, it cannot directly look down because everything will come back at the same time. So it has to look at side. So side, it sends there, 37 degree, twing, it bounces back. Now things that are close sends a pulse that is comes early. Things that are far sends pulse that are very late. You can see that. That's a very amazing animation from NASA's side. You can see like each pulse is taking time. There's sweet time. The basically near thing will give you a near ping, far thing will give you far thing. So now you have that data, useful data. That's why whenever you are talking about basically synthetic aperture radar, most of the time, not even most, 99% of the time, it will always be side firing. Meaning even if you are putting on a plane, I'm a plane, it's going to be like firing here or there. It will never be, I'm looking down. It's not optical. It has to look at side. So that's why it's generally also classified as side firing radar. It has to fire. So if you are seeing the satellite going on top of you, does not mean it's scanning you. It means it's scanning something that is 423 kilometers there or there. Again, it can change its direction. So it can left side or right side. That's up to them. But it will always be basically the band that is scanning. It's 433 kilometers away. Now be mindful, the satellite is two-dimensional, meaning it's doing a two-dimensional sweep. Think it this way, how you have a scanner, it has a white line that goes through, exact same thing. That is the line that satellite is doing. The line width is around 242 kilometers, and because this puppy is working very fast, it's a very high resolution data. So swath, which is that offset, like from orbit offset is 423 kilometers. Now this puppy is full resolution, meaning it's not throwing away data. Back in the days, we had the technology, we knew the principle, but the computation was not enough. You can see that like L band and S band, it has so many antenna modules, and you can see that S band is smaller. Why? Smaller wavelength. L band is bigger wavelength, and it's collecting all of them simultaneously. So the resolution wise, it's awesome. Now how the heck they are doing that, all this managing thing? This is their time graph, German engineering. So what the red spots are where this puppy is yelling. It's like, it's yelling there. So why it's yelling? Of course, it's an active system. It's not just listening to radar, because again, land does not emit radar. It's emitting that. So every red pulse that you see is blasting out. Now, once you blast it out, that pulse goes to the main reflector, reflects to the ground, and then it stops. It's like, okay, I did my job. Now it waits for bounce back. Now bounce back will happen, and again it will come back to multiple antenna array. Basically there are 12 rows of basically L band and multiple rows of S band. So each band, it will give you a data. Basically each of these antennas are focusing on one patch. Basically take this 242 kilometers, divide that area into like this 12 sectors. Each sector is taken care by one antenna. Basically one antenna is like, okay, I'm listening to it, so it does not get overwhelmed. That's why. Otherwise, like back in the days, this was also done very slowly. It's like this. It was zigzag, very low resolution, or they had to make the slice very thin or resolution too low. This puppy has all. It's like, I got this. That's why it has so many antennas. And again, it's also collecting the phase data. So not only is just like I am collecting data, it's like what happened to that radio wave. That can tell you a lot. And given the fact that you have two radio waves, so both of them will interact differently to everything. Basically, if it goes through a leaf, it's going to react different. If it goes through sand, it's going to react differently. If it goes through something that has a lot of potassium, it's going to react differently. A lot of nitrogen is going to react differently. And you have two data points. So you could have a scenario where something is behaving erratically, but the likelihood of both of them messing up is 0. So that's why 2-band gives you precise data with that polarization data vector. So now you have distance, you have location, and you have intensity. Intensity is also very interesting here. It's almost like LiDAR has extra vector nowadays. Basically, you yell, you know how much power you yelled at. So you know that power, that pulse power, you know. Okay. Now you got to wait for the return data. Once you got the return data, you stop the clock. You divide that by basically light speed and half it based on the time. You calculate the distance. Awesome. Now here's the deal. How much energy should come back? Now you apply another formula which we call inverse square law. Basically, you send, let's say, 1 kilowatt of pulse. How much should come back based on inverse square law? You already calculated the distance, you did the math. So it's supposed to be, let's say, 1/100th of what I sent, but you receive 1/500th. Okay, that's one vector of data. You just store that. Another spot of land. Now that sends 400 back. That means there was something different there. So not only you have two-dimensional data where it's like this is height map, you are also saying what is there. Is it something that is reflecting a lot of light, as in like a lot of photons perfectly, or is something that is absorbing photon perfectly? And again, L band and S band will behave differently. Combine both of data, now you know a lot. So this is a 4 data vector system: distance, location, intensity, and polarization. And given the fact that you are receiving both of that, all of that data in L band and S band, now you have a ludicrously high data rich scan. So this also comes back to the core factor, like how the heck radio behaves with something. Like when we are talking about, like we talk about how reflective something is, like, emissivity, albedo. Whenever you are talking about radio, things change, things go to relativity, permeability is weird names. Basically, I like the better word, scientific word, dielectric constant. So you can tell, like, hey, this is the leaf, this is the dielectric constant, this is sand, this is the dielectric constant, this is dried wood, this is the dielectric constant. That is the key data. So you have all this data in 2-band going on a large spot. And given the fact these antennas are awesome, like back in the days, one of this antenna unit would have been used as a satellite. They have and that's why I specified it has so much power, 6 kilowatts of power. This puppy is dense, meaning it's going to give you a data and it's like, I know what is there precisely. And it can double check it from itself. It's like, hey, how did L band react? How did S band react? And NASA can literally have a field of stuff. They could like literally put a patch of sulfur and it's like, how the heck sulfur reacts? Okay, now we have that data. How the heck dirty water reacts? Now we have that data. How the heck crude oil reacts? Now we have that data. Now that will help them whenever they are going through something where there should not be oil spill and randomly they have oil spill. They are like, we calibrated that data. So they know that it is oil spill. They can take action very quickly. So technology is awesome, German engineering. And here's the deal. If you have noticed, all of these are equally spaced apart, like 606 microsecond, not millisecond, microsecond. This puppy is fast. They realize that from a temporal point of view, it's creating a line. Basically, it's not doing anything when it's yelling. So they realized, what if this gap, basically that 606 microsecond gap is switching? They can change it from 606 microsecond to 605, 608, they can switch it. So meaning if they are overlaying 2 images, they will not even have that blind spot. Perfect German engineering. They're smart. Then we come to, why the heck bother with that much hula lala? Well, the reality is this works at 24/7 all weather. Weather does not matter to it, just goes through it. That's why they are spending so much money into it. And it's an active observation satellite, meaning not only is just like I'm looking at something, it's also giving you feedback. Meaning if you are going through an area that's not supposed to be the way it is, you can change your parameter. You can be like, hey, this patch of land is behaving erratically. You do not want to actually send someone there, or maybe it's some other country. How the heck you gonna scan it? Change the parameter. Basically, how loudly you are yelling, change it. Based on that, it will behave differently. That characteristic, that feedback loop will help you to fine tune. Like, I know this is exactly there. That's really awesome. That's why active observatories are desirable. Then it has 4 data vector that I already specified with 2 spectrum, 1 fine resolution, 1 large resolution. So all the data spectrum multiplied, that's like 8 data spots per basically per pixel. So that's awesome. It's high spatial resolution and temporal resolution. It's scanning the whole goddamn planet every 12 days. That's fast. And it scans through vegetation while scanning the vegetation also. It's like, okay, I'm going through a forest, I can study the forest floor while also telling like how healthy the trees are. That's why I specified having two wavelengths while retaining the basically polarity data helps you figure out all of those things. Leaves behave completely differently one time, completely different other time. And you can figure out, hey, this forest is about to die, send someone there to take care of it before it's too late. That can be done. That's why vegetation. So, and not to mention, if you overlap two images, which is they will keep talking about, you can do interferometry. And this benefit is like you can see wavelength wise 6 centimeter plus and minus, meaning it can detect soil, it can detect land mass moving, and the movement resolution is in centimeters. That's mind-bogglingly awesome. Like back in the days, if we achieved meters, that would have been like, whoa. Now this is so fast that you can see a volcano erupting. Like again, that's why I say the other data, that polarization data and informatory data can allow you to see this sort of thing. You must have seen plastic bending and this thing happen. That's the data. You can use that data to figure things out. It's like if volcano is like slowly rising, you know, like it's slowly rising 1 centimeter per month, but it randomly, the speed of rising starts to go up. This satellite will like, whoa, 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 bro, something is serious here. It will look very weird and you're like, it will trigger a red alert. Very useful. So what does it mean for public, for you and I? Well, here's the deal. The data is open for public. What does that mean? That simply means once the satellite collects the data, it's a huge chunk of data. It goes through the server, gets through the processing, gets to the archive, then it's open to public, meaning you and I can open it, meaning every university student anywhere on the planet can open it as long as they have internet access. So no North Korea, pardon me. Everybody else can get it. So it's open for public, and they have enough wisdom to realize that there are bad things known as natural disasters or disaster. In those sort of time, they will bypass that time. Basically, how long it takes from data from servers to archive, they will shorten that time to very quickly. So what does that matter? That matters, think this way. Let's say earthquake happened, bad earthquake, and let's say it's followed by bad rainstorm. How the heck you gonna see what the hell is happening? This radar is like, I got you. And because it has data from last 12 days, as in like, you know, previous slice, it can compare that and it can tell you this road is intact, this road is not intact. You can save so much time. Time matters in disaster. So you can say flat out before people are dispatched, it's like, bro, do not send people through this route, send it through this route. This route is intact. Majority of the route is known. If you have landslide, do not send it through here, send it through there, and it can walk any time of the day, any weather condition. That's priceless. You can figure out like how many buildings have collapsed, how many buildings have not collapsed. All of data would be available. That's mind-bogglingly important in a disaster scenario. So at that point in time, the data will be fast forwarded. Then it's focused on land, because we had satellites that are focusing on atmosphere. We had satellites that are focusing on basically emissions. We had satellite focusing on sea life. This puppy is land, like basic land. That's why we can learn a lot. Like again, it's so amazing that you can take look at tectonic shift, like, oh, tectonic shifted this. That's how amazing this puppy is. And one of the primary reason why ISRO is investing so much money, again, it's helpful to everybody. It will allow India to study underground water table. That's like, how the heck you can do it? Here's what is constant about water tables? They recharge in rain season. Okay, so you scan the data for a year. Rainy season, you will see ground swell up, because again, water is not, you know, spaceless. It takes space when it's underground and it is under pressure, so it does have a pressure exerting upwards. So once you drain it, let's say somebody drained it, awesome, it sinks, the ground sinks. It's very little, it's few centimeters, but this satellite can detect it. So you can detect every pass, you can detect. It's like, is it sinking at what rate? And then you're like, okay, in rainy season, is it rising at what rate? Is it balanced? You can figure out a lot about underground water reservoir, and you can detect a drought before it happens. And this can also help you to like, hey, this area really not recharging as it should be, let's turbocharge rainwater harvesting, or do some scanning why the hell it's not happening. You know, it's a very amazing tool from that point of view. And we have IceSheet. Again, IceSheet is a very weird thing to study in optical spectrum, but in this spectrum is like, bro, I can tell you how ice is moving. That's desirable. Landslides, awesome thing. Forest health with ecosystem monitoring. Because it's not just gonna, oh, there is a forest. It's like, this is the forest health, and they can do you know, healthy scan, bad scan. They can figure out all the data. Again, two spectrum, both feeding to each other with polarization data. They're like, we can tell you the health, age, everything of the tree. So forest health would be monitored throughout the planet. That's awesome. And ecosystem monitoring, because again, you are studying the whole ecosystem. And this is a very good example of why this matters. This is a volcano eruption. Okay, things happen. Cloud. Now what happens if something is here, something bad happened here? Let's say there was a town there. How can you scan it? But here's the, in optical, it's a blind spot. In spectrum, you can just see it. In radio spectrum, you can just penetrate it, stand it, and you're like, hey, all the roads are intact, just send people. Don't worry too much. Hey, bro, don't send the people, roads are damaged. That's awesome. That's like, shut up and take my money kind of awesome. This is how C will look. Basically, C just does not appear, flat out does not appear. So it's an amazing tool for public. So this was my presentation on basically NASA's and ISRO's marriage. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.